Welcome to Introduction to Radiographic Imaging, presentation on image formation and radiation safety. This presentation will be the primary resource for this information with the intent to provide you with an overview of the physics of radiography, an introduction to how a radiograph is made, and a very basic review of radiation safety. We hope this information will aid your understanding of the radiographic image when you are learning the normal radiographic anatomy. In this course, you will need to understand the making of the image and be able to define and know how to achieve the Alera concept. While you will not be tested on the specific physics concepts in this presentation, many students still find it beneficial to understanding a little bit more about the image when they then go on to study the normal anatomy. Future imaging courses will definitely build and elaborate upon this foundational information. As you review the presentation, you should use the self-guided exercises to work through the learning objectives. Let's start by defining an X-ray. An X-ray is a form of electromagnetic radiation, which is a combination of electric and magnetic fields that travel together in the form of a sine wave and have both frequency and wavelength. The image on the right shows the electromagnetic spectrum, and you can see that X-rays have a higher frequency and a shorter wavelength than visible light and ultraviolet radiation. X-rays are produced in a vacuum tube, which is housed in an X-ray tube. And in that vacuum tube, we have a filament, which is known as the anode. We need to heat that filament, and when we heat it, it produces electrons that boil off and kind of hang around it in a cloud. We have to put a current on. And for those of you who have helped take radiographs, this is your MAS setting on the X-ray equipment. We have to then accelerate those electrons across the vacuum tube with a potential difference toward a target that's also known as the cathode. And this would be the kilovolts peak, or the kVp, that we use on the equipment. Those electrons then interact at that target and they produce a vast amount of heat, which has to be taken care of by your housing, and a small amount of X-rays, which then we allow to be directed out of a window in that X-ray tube. X-rays share a lot of properties as other on the electromagnetic spectrum, properties such as not having mass, traveling at the speed of light, being invisible and not being able to be felt, traveling in a straight line until acted upon, and not being able to be deflected by magnetic field. Some special properties of X-rays include that they can penetrate all matter to some degree, that they can cause certain substances to fluoresce, that they can expose photographic emulsions, and that they can ionize atoms. X-rays will interact with matter somewhat similarly to how light photons will interact with matter. They can be absorbed and they can be reflected or scattered. But more importantly, they can also pass through the patient's body. Now, once they pass into the body, they can be absorbed or scattered by deeper internal structures, but importantly, they can also pass through unchanged. It's that passing through unchanged that is going to be important in this basic concept of making a radiograph. So this is just kind of illustrating that we have to have an X-ray tube, and within that tube we are going to create that X-ray beam. Now that X-ray beam has to be directed towards an image detector, and in the bucky tray of this table is an image detector. Then in order to get a diagnostic image, we put the object to be imaged within that path. So it has to be placed between the X-ray tube and the image detector. The most important thing to remember is that our radiographic image is possible only because of that differential interactions and absorptions of the X-rays by and within the patient. And so ultimately, a visible image of the internal makeup of the object is what we end up with. So in order to have that visible image, we need to have a method of recording the image, and that is our image detector. So here's a schematic, X-ray tube here. We create the X-ray beam. Notice that the X-ray beam actually flares out as it gets farther from the X-ray tube. We have our image detector. We put our object to be imaged, which is the dog foot here, within that X-ray beam. And then as some of the X-rays get absorbed, but some of them pass through, we get a pattern of blacks, grays, and whites on our image detector, and that is our visible image. There are a few different methods of having a way of getting that image, and we're going to talk about those now. So conventionally, we used film and screen radiography, and so that is having a piece of radiographic film that's very similar to photographic film, in which there are chemical reactions that take place in response to the energy that's added to the film emulsion. And the energy comes from X-rays and visible light. It forms a negative image on that film, which can then be developed. So the film is also coupled with an intensifying screen, and that intensifying screen is actually something that will fluoresce when the X-rays interact with it. And that fluorescent light, the visible light, is then what exposes the film. Those together are housed in a supporting cassette, and that gives us our film screen radiography. The film, once it's exposed, has to be developed, and then we get an analog image. Here's an example of boxes of film, come in various sizes. There are cassettes then that match the various sizes. The film is placed within the cassette. Because the film is sensitive to light, we do that in a dark room where there is no visible light. Once we expose the film, then the film within the darkroom has to be processed in a typical tabletop processor here that a small animal practice might have. And it is developed. Once it's developed, we get a sheet of film that has our image on it. That is now what we call our radiograph, and then we can view it as an analog image on a view box. Much more commonly now, we are moving from film screen radiography into a form of digital radiography. And there are two basic forms. So the earliest one was computed radiography, where our image detector is actually an imaging plate that can trap that X-ray energy on a photostimulable phosphor that gives us a latent image. That imaging plate is in a cassette, very similar to film screen radiography. That imaging plate, once it's exposed, is then put into a reader that scans it with a laser beam to get us an electrical signal, which then can be turned into our digital image. Those imaging plates can be cleared and reused thousands of times. So here would be kind of a typical setup for computed radiography. We have our imaging plate here that is housed within the cassette. They do come in various sizes like film screen radiography. This is sensitive to light, so it has to stay in the cassette. The imaging plate is exposed, and then once it's exposed, we put the cassette inside the reader. The reader extracts the plate, has the laser beam scan it, and turn that into the electrical signal, which then is turned into a digital image. So this is a quality control station. And then a big benefit is we can send that digital image anywhere, and specifically we will send it to a computer workstation where we have software and we can manipulate and view it. Probably the more kind of state of the art, going beyond computed radiography, is digital radiography. And how that differs is that there is a special digital panel, which is a solid state detector, that is either directly connected with a cable to a computer or can provide a wireless signal that can be sent to the computer. The big thing about this is that there's no reader step needed. So our X-ray goes directly to a digital signal. This makes it very fast as well. So this would take about 8 seconds to produce an image compared to 60 to 90 seconds for both film screen radiography and computed radiography. This digital panel can also be reused, and again, we end up with a nice digital image that can be viewed and manipulated. So here's an example of a digital plate within the table that is directly connected by a cable to our quality control station, and then that image or that digital image can be sent to a viewing workstation. Here is our setup in our small animal hospital, where the digital plate is within the bucky tray of this table, and then it sends a signal to the quality control workstation here. To finish up, we're going to talk just a little bit about radiation safety. So we said that one of the important properties of X-rays is that it could ionize atoms, and it's those ionizing properties that can render them hazardous. And so we need to think about the safety that goes along with that, because ionizing in DNA can lead to some things such as increasing rates of mutation of cells, causing abortion or fetal abnormalities, causing increase in susceptibility to disease and shortened lifespan, giving individuals a higher risk of cancer, and inducing cataracts. Now, in veterinary medicine, we have to think both about our patients, but we also have to think about our staff, our personnel, who oftentimes are in the X-ray suite while we are obtaining and making radiographs. So our goal needs to be to obtain a maximum diagnostic information study with minimal exposure to our patient, our radiology personnel, and our general public. And if you can just remember this one slide for radiation safety, it's going to be what will get you through a little bit of time here. So that is our ALARA concept. And ALARA stands for as low as reasonably achievable, which means keeping our exposure as low as reasonably achievable. There are 3 practical rules that we can remember to keep our radiation exposure low. And that is 1, thinking about distance. If we can increase our distance from the source, we actually will really decrease our exposure. So image on the top here actually shows ways that we can do that. So for one, here is our imaging plate, and the personnel staff member here is actually holding that plate not with their hands but with a plate holder, so that gets them further away. Another method is this X-ray tube. When we expose it, there's actually a 6-foot cord, so when she's actually ready to expose the image, she can step away from that X-ray tube by 6 feet. So those are ways to maximize our distance, get as far away as possible. The second rule is to remember time and to reduce the duration of exposure. There are a few ways to do that. So one, we can reduce the duration of exposure by keeping our seconds, our MAS seconds part, really short, so have a short exposure time. That's good for both the patient and for the personnel. Other ways that we can reduce personnel exposure are ways of kind of positioning the patient without us having to be right nearby and holding. So this is a sedated patient, and we can position them using some special devices. And another way is to actually rotate your staff so that each staff member has less time, making radiographs. So having more staff will allow them to rotate through and be exposed for a shorter amount of time. And then importantly, we also should think about shielding. So personal shielding, and that is using protective lead barriers between you as a staff member and the radiation source. And so those would be lead aprons, lead thyroid shields, and lead gloves. And you can see that the staff members taking the X-ray on this horse all are wearing lead aprons. The ones who will be anywhere near the X-ray beam will also have lead gloves on, and then wearing lead thyroid shields would be important as well. Now keep in mind that lead will only protect from scatter radiation. It does not protect from the primary beam. And this is an example of that. So this rectangle will be where the primary beam is. This is a dog that is having a positive contrast study of the bladder and the vagina. And the staff member who is injecting the contrast is kind of trying to protect themselves with lead. However, if you look closely, you can actually still see the hand, the soft tissues, and the bones of the hand, even though there is lead. And that is because lead will not protect from the primary beam. So please keep that in mind.